I discuss with you section 9.2 dual graph. A plane graph G partition the rest of the plane into a number of connected regions are called phases of G. Here we define the phases of G. Consider this figure. In this figure, uh, it has six phases. In this figure, this is the example for uh, phase of graph. Now we shall denote f of g or phi and phi of g respectively, the set of all phases and number of phases of a plane graph G. Each plane graph has exactly one unbounded phase called exterior phase. F1 is the exterior phase of the graph. That is, F1 is the uh, exterior phase. So we are discussed about the phases of the graph. Now a theorem. Let V be a vertex of a planar graph G. Then G can be embedded in the plane in such a way that V is on exterior face on the face of the following of the embedding. So we denote the boundary of phase f of a plane graph G by B of f. If G is connected, then B of f can be regarded as a closed walk in in which each cut edge of G in B of f is transversed twice. When B of f contains no cut edge, it is a cycle of G. In figure, uh, figure B of f, uh, B of f2, V1, V1, E3, E3, V2, E4, then E5, V4, E1, V1. So this is a cycle. Another it has then next B of 5, this V5, V5, E10, V5, E11, this V8, E12, V8, then again V8, V8, E11, V5, V5, E8, E6, E6, then E6, V6, V6, E9, V5. So this is a another example of cycle. A phase F is said to be incident with the vertices and edges its boundary. If E is a cut edge in plane graph, just one face is incident with E. Otherwise, there are two faces incident with E. An edge separates the faces incident with it. The degree dg of f dg of f of a face f is the number of edges with which is incident c, which is incident, that is number of edges in B of f, cut edge being counted twice. Then now we define dual of graph. Let G be a plane graph. One can be defined G star as follows. That is, corresponding to each face of G, there is a vertex F star of G star. That is, a face of G, there is a vertex F star. Corresponding to each edge, the E of G, there is an edge E star of G star. Two vertices F star and G star are joined by the edge E star in G star. If and only if their corresponding faces F and G are separated by the edge E in G. This graph is called dual of G, that is G star. G star is the dual representation of G. Now consider the example. Here it is the representation of G. This is the graph G. Here the exterior G region is F1 and F and another faces F2, F3, F4, F5 and vertices and edges E1, E2, E3, E4, E5, E6, E7, E8. Then what is the dual of this graph? So this is the dual of the graph. It is the dual of the graph. Dual of G star of a plane graph. G is planar, and when G is connected, then G star star isomorphic to G. Isomorphic plane graphs may have an non-isomorphic duals. The following relations are direct consequence of the definition of G star. V of G star equal to V of G. V of G star equal to phi of G, and epsilon G star equal to epsilon G, and d G star F star equal to d G F. That is the degree of both dual graph and graph are same for all F belongs to G. Then next is a theorem. If G is a plane graph, then summation F belongs to F d of F equal to 2 epsilon. So we have to prove that the summation of degree of F is 2 epsilon. So let G star be the dual of G. Then summation F belongs to F of G d of F equal to summation F star belongs to V of G star d of F star. This is equal to 2 epsilon G star. So we get 2 epsilon of G. If G is connected plane, then V minus epsilon plus phi equal to 2. If G is simple planar graph with V greater than or equal to 3, then E epsilon less than or equal to 3V minus 6. If G is simple planar, then D delta less than or equal to 5. If case 5 is non-planar, and K33 is non-planar. So here I discuss with you section 9.2 dual graph. Thank you.